So we're gonna get started officially. So we are very excited to have May here today. You see her there. Could come talk about one of the, in my opinion, like the most fascinating technologies in the whole world, which is GPU. So I'm sure that pretty much all of you guys would agree with me after this class. I will introduce her a bit more later on, but just a bit more about our program, where the program's name is Create and Learn. I'm sure many of you have been taking classes with us together already. Most of our classes are in small group classes with only 3 or 4 students and a teacher. We do very interactive learning. You know, this is a special kind of classes we run where we invite industry expert like May and to talk about cutting edge technology, so you see how the technologies actually works in the real world. So I'm going to introduce May very briefly. So she's going to introduce herself a bit more, but she's a senior scientist at Nvidia. She has been doing a very, very interesting work in areas that are related to government. I'm going to have her tell you a little bit more about it. Nvidia is also, I would say, the very top company in the world that building these technologies, and not just for artificial intelligence, but also in places you may not realize, in movies, in video games, and a lot more. So with that, May, would you like to get started?
Okay. All right, let's get started. We have a lot to cover because GPUs can do a lot of different things. So I'm going to introduce myself. Like Jesse said, my name's May. I'm a data scientist at Nvidia. I'm also a mom. I've got kids. The oldest one's probably near one of some of y'all's names or ages. At Nvidia, I do a bunch of different things. And today, what I thought I would do is talk about what a GPU is and where it gets used and how it sort of relates to AI. Video games, GPUs, we're going to learn about ray tracing, and then how all of this comes together in AI or artificial intelligence and why GPUs are useful for that. Okay, so you guys can just type your answer in the chat. What year was the first video game created? So you can do A, B, or C. Okay, I see some B's, some C's, some A's. Seems like a mix. Maybe more C's, which is good because C is correct. Oh, too fast. 1951, and this doesn't look anything like a video game you would see today, right? This is more of how can a person interact with a computer and get some sort of visual content back, meaning they're playing with it with some sort of visual information. And then a little bit later, there was an even, it would be considered more sophisticated visual game called OXO. This was done by a PhD student, I think in Oxford, but I can't remember. I think it's Oxford. And then, you know, things got a little bit better, right? Pong on the left, this was a really big breakthrough because you could play against a computer and things moved. And then Super Mario Brothers came around. Has anybody ever, have you guys played these games? Are you guys familiar with these games? But still pretty simplistic, right? Then things got even better. We got more of a 3D perspective, right? This is Mario Kart. I used to play a lot of this when I was a kid. And this was awesome when I was in middle school. It looked incredibly real. But what do you guys think of video games nowadays? Like, what do those types of computer graphics look like now? They don't look like what they used to, right? This is actually a simulation. This is done by a game engine called Unreal. This is their newest version, Unreal 5. And so this is what game developers use to build video games. And things have gotten super realistic, from the lighting to the dust in the air to the way people look. Skin looks realistic, hair looks realistic, rocks. All of these materials look really, really real. And sometimes it's almost hard to tell if it's a computer game, right? Okay, so here I'm gonna play a quick video. And just kind of up front, all of my videos are very, what we call high resolution, because we're the graphics company. And so They're high resolution on my computer, and I'm hoping they come through on the Zoom. But if they're a little laggy, I'm sorry. We can maybe send some links out in the, after the fact that kind of show you where the originals are. But here's one. So this is what we can do today with new graphics. I know it's a little laggy for some folks, but just when you can, when it does sort of come together, pay attention to how complicated this scene actually is from a graphics perspective. There's a lot of light. There's a lot of surfaces that reflect light. And so just pay attention to that while you're watching it. We'll move ahead a little bit so that we can get through it a little bit. Okay, so that was actually a video clip that our group put together at Nvidia. I'm not a video game person, so we might have actually taken some of those characters from other games. I saw people trying to figure out what game it was, but I'm not positive. But the amazing thing about that is that was run on one computer. And so we're going to talk about how you actually would do something like that and what does it take. So what do you guys think is making things look so realistic in that video? You guys have any ideas? Oh, I saw computer graphics and lighting, computers. So I saw ray tracing. I might have given you a hint with my intro. Lighting, better GPUs. That's a good guess. Man, all sorts of good guessing. All right, so before we kind of get into what part of the computer is really making this look so much more realistic, we're going to talk about what does a computer do. And I know a lot of you guys probably already know this because you're here and you're using computers. But just so that we are all on the same page, basically a computer essentially does 4 different things, right? It takes input information, it stores that information, it'll probably process that information, and then it outputs that information. Just 4 basic functions, but from there things can get really, really complicated. So you input information by different ways, right? We type on the keyboard, we use the mouse. People play video games now, so you can hook up controllers. Maybe you speak to your computer. When you store information, that's usually stored on disk. We put it in files or in memory and RAM. To take that information and turn it into something, we'll use a CPU, right? So this is the part of the computer, the brain, if you will, that processes the information you're giving it and storing on it. And then if it makes some decisions, or you process the information and now you have new information, you want to output it. And so it'll put it on the screens. I guess you could also say it would write it to files. You could hear music, and now even VR, right? Virtual reality is a possibility as somewhere to output information. So if you know all of that stuff, we didn't really, none of those things necessarily answered the question, what do you think's making things look that much more real? But a lot of you guys had the right guess. And it should be obvious because I'm from the company that makes the GPUs, right? So it's the GPU. The GPU is the part of the computer that it basically manages all of the graphics and video workload, right? So what we're gonna learn in the next couple slides and for the rest of the hour is how complex that type of work is to actually do on a computer. And as graphics grew and got more complex, like we saw how those video games got more complex, it became too much for one brain to do, right? And that one brain that existed before the GPU was just the CPU, right? Where CPU is central processing unit. The GPU stands for graphical processing unit, so with the G. And so its whole purpose in life originally was to take all of the work that was requested of the computer around graphics and do all of that work so the CPU didn't have to. And so we've been doing this for about 30 years, NVIDIA, building graphics chips. And this is our newest one. This is called the Ampere architecture. And we just came out with it last week. We've been working on it for 3 years. And this little piece of silicon, it has 54 billion transistors on it. That is a huge number. Now this is a big picture, but this card, this whole module here, is about the size of an iPhone. So, and then the silver part where you see NVIDIA, that's underneath that is this gold looking bit, and that is the chip. And that thing has 54 billion transistors on it. Now, to get an idea of how big that number is, there's 7.8 billion people in the world. And I just said there's 54 billion transistors in a chip. So you would have to take the world's population and multiply it times 7 and then shrink it down, each person, and then fit them on a chip. And so this is a very complex piece of engineering, and it is incredibly hard to make, and that's why it took us 3 years to figure out how to make it. Yes, it is a lot. 54 billion is a lot of transistors. And if you don't know, the transistors are small little components of circuit boards that you use. It helps the computer keep tracks of ones and zeros. And so the more different ways you can combine ones and zeros, the more complex type of task you can tell a computer to do. And so the more transistors you have, the more complex things you can do generally. But that's great and all, but I already had this brain, I had this CPU. Let's talk a little bit about what's actually different. We know the GPU is taking the video and the graphics load, and we needed it because things got too complex. But if you look at these two sort of pictures, I got a CPU here on the right and I got a GPU on the left. What do you guys see as different between those things? What do you think the big difference is? That it provides visuals. There's more tiles. CPU has less transistors. I saw more cores. That's good. It's old. The CPU has less tiles. Yeah, so let's talk about these tiles. So the tiles are what we call cores. And you could think of those as the brains, right? And so you need all of these brains to do different types of work. And we're going to talk about that in a minute. But the big difference to take away here is the CPU has multiple, but not as many brains as the GPU, but they're different. They're slightly different. They're shown here different in size, but it's better maybe to think of them as the CPU brains are a little bit, they do something different than what the GPU brain is being asked to do. The GPU brain's a bit more specialized, and because it's more specialized, we need more of them to get the job done. So if you could think about maybe what do you think, why do you think we need so many cores to do the graphical work on a computer? You guys have any ideas? Why you think we would need more little brains? Little might be a bad word because they're pretty impressive. more cores, the better graphics. To get the job done, that's very short and sweet, better graphics. Graphics are very complex, that's correct. That's correct. All right, well, to kind of understand this concept, you kind of have to think about what type of processing, what type of computation are you asking your brains to do? And there's two main types of processing typically that you ask a computer to do. There's serial processing, and that's very simple. I want you to do these things in this order. So you do this first, and then this second, and then this third, and this fourth, and this is how we solve the problem. I'm telling you the instructions processor on how to solve the problem. And so if you only have to do one thing at a time, then you only really need one processor. If I added another processor to this picture with the way we set up these instructions, it wouldn't help me at all. But if you have a problem that you can divide up, and I can say, I can actually get this done if I divide up the work and have more people helping out, or more brains, or more processors, or more cores, then I can attack this problem in parallel. And it turns out graphical rendering is a parallel problem. And there's lots of different ways to build graphics on screens. But one really cool way that Nvidia just made feasible in hardware, this was a really challenging problem until recently, is a concept called ray tracing. And so to get to the ray tracing, we're going to go to a video. So I'm going to try here.
Ray tracing, in contrast, is trying to do a physical simulation of light. And the way to think about it is, you know, we live in a world where light bounces all over the place, and it hits on an object and bounces around, diffusing, diffracting.
Subsurface scattering, things like that.
All kinds of stuff, right? But eventually, one ray of light makes it into your eye and hits your retina, and that's what we perceive as vision. So what ray tracing is all about is pretending that you're kind of modeling how a retina works, and you project forward into the scene, trying to figure out what other rays have hit the object that's lighting your eye. So ray tracing is all about the physics of light, and when you do that, you get rid of all this artistic interpretation that happens with traditional rendering techniques. Yeah, so it's very much the way movies do, generating CGI, and now what's really different is that we're able to do that in real time using RTX.
Okay, so ray tracing. So hopefully, if you caught some of that, ray tracing is this is a mathematical problem where you're trying to simulate how light interacts with a scene, and how your eyeball, your retina, sees that light. That's how we visualize the world. Light moves in waves or particles, but you can simulate it with a ray, which is just the trajectory, the line in which the light moves, and then it hits objects and bounces off. And the same thing, and it can bounce off other objects and then back on the object. It can go through the object. Light can interact with objects in a very complex way. And then you can move your camera around. Where are you observing this light bouncing around? It's going to change how much shadow you see or what colors things look like. There's all sorts of complications that actually end up dictating what the scene looks like. And if you look in this graphic, this big array, this big array over here, this is essentially an image. This is what you're, oh, sorry guys. This is what you're trying to get the computer to create. You want the computer to look at this scene the way you've described it, and all of the light that's bouncing around in the scene with hitting different materials, and then the camera is looking at a certain area. What would that camera see? That is the act of rendering, and being able to do that in real time, or even at all, is really, really challenging, because if you think back to how we were talking about parallel processing, this is a parallel problem. If I only did one pixel at a time, one of these little grid spots at a time, the image would only show up one pixel at a time, and movies would be very slow, and this whole situation would be very slow. All of the imaging would be very, very slow, and it would be hard to understand, and you would probably get very impatient, right? But if you can render the entire image at once, all of these pixels at once, then we're in business. Then we can start making movies, right? And so that's where all of those little brains in the GPU come in handy, because I need to essentially do a parallel problem. I need to parallel render a scene using ray tracing. And basically this boils down to a whole bunch of math that the GPU is fantastic at doing. That math can be applied to other things, and we're going to get into that in a minute, but at the its sort of basis, that is those little brains in the GPU, specialized brains, are very good at a certain type of math that allow you to parallelize image rendering. And so one game, which I saw you guys talking about a lot, that we could talk about is Minecraft. Now, Minecraft doesn't necessarily look like those games I showed at the beginning, because the way Minecraft is played, you all get to decide the story, right? You plop into the environment and you get to build things and decide what things look like, which means that a computer programmer doesn't know beforehand. So it's really hard to tell a computer graphically how to do that before we had real-time ray tracing, because otherwise you just had to do what's called an approximation. But now with ray tracing, we can render realistic lighting and graphics, even in a game that we don't know how it's going to unfold, because you guys are deciding as you play. So we're going to play a little video that shows the game Minecraft with ray tracing. All right, so you guys kind of seeing the difference here when you can actually render light realistically? Okay. All right, so now I've got another example of what we can do when we can ray trace. We can ray trace, we can create games. I know Minecraft is a bit different in that it has this very blocky world, but you can also create really realistic worlds and then actually play with it in real time. So this is a game that Nvidia created to kind of highlight some of these capabilities. And this is being done on a single GPU, just one of those things that's basically the size of a cell phone in the computer. think the thing to think about when you're watching this, that was in real time. So somebody was the gentleman you guys saw at the keyboard. He was playing in this game, and this is a game that we created just to show off sort of how real-time ray tracing can make a game seem more realistic. So nothing about that game was pre-computed. The game designer didn't know where the marble was going to go because somebody's controlling where the marble goes. So you can't pre-compute what the lighting is going to look like or how the shadows are going to project onto the surface or anything like that. But in order to get super realistic and make things look real, ray tracing is the way to do that. And it has just been incredibly hard because it's such a compute intensive, meaning you have to do so many calculations that it's been impossible until about a year ago with some of our GPUs to be able to do it. And as we've come out with new GPUs, you can now do this on a single card in real time. And we can go back over ray tracing if you guys have some questions about that in the Q&A if we have time. But it's pretty amazing that that's what you could do in real time. So we've talked about the GPU and how it's fantastic at making these realistic images, and it uses this concept of ray tracing to make them. But remember when I was talking about all of the math? You guys have probably heard GPUs and AI used together. And so now we're going to try and we're going to make a bit of a jump, and we're going to talk about what about all that AI stuff? Why is this thing that's so good at making graphics and video games look good and movies look good also used for AI? Okay, well, you remember all of that math I was talking about? All of that math, it wasn't created for video games. It was created just as math. And it turns out the same type of math that you need to do graphics rendering is super useful for training AI models, specifically neural network models, which is what we're going to talk about next. And because those are such large computation problems, all of those specialized cores or brains are immediately useful for training AI models. So we're going to talk about deep learning, which is a type of AI. And if you guys know what deep learning is, we're about to talk about it, but I thought maybe I would ask if any of you guys have any ideas of what kind of things you would use deep learning for. Even if you don't know what it is, maybe do a guess. Hard math, that's accurate. It is for hard math. Does anybody else have any other ideas? Minecraft. A lot of Minecraft talk. Drawing, Roblox. Trig, is that maybe trigonometry? I'm not sure. Okay, so we're gonna do a little crash course in deep learning, which is a type of AI. Okay, so in deep learning, let's say you have some type of data and you know what the data is. Maybe it's a pile of cat pictures and dog pictures and bicycle pictures, and you want to train a computer to be able to say, that picture is a cat, that picture is a dog, that picture is a bicycle. Now, how are you going to go about doing that? Now, if you're going to use deep learning, there's a pretty simple way of doing that. So you start with a training data set. This is called labeled data. It's very important. It means you've taken your data and you've given it a label that tells the computer what it is. And then you need a model. The type of model that deep learning uses to do this type of task, which is a classification task, is called a neural network. It looks like a network, things are connected, but this is basically the mathematical model that the computer needs to learn how to decide whether or not a picture is a dog or a cat. And in the beginning, this model doesn't know anything. If you give it an image, it'll just spit out a random number. It doesn't know what a dog or a cat is. So you have to do something called training. All right, and training is where you feed this model, you program the model to start looking at all of these pictures of dogs and cats and bicycles. And you do this, you code in what's called a deep learning framework. You guys might have heard of some of those. But this part of the process is you just continuously show the model pictures and you say, this is a cat, this is a dog, this is a bicycle, here's another cat, here's another cat, here's another dog, here's another dog. And it makes at first guesses. I think this is a cat, I think this is a dog. And sometimes it might be right and sometimes it might be wrong, but you correct it because you've given it the labels. It can go and check, it can make a blind guess and say, okay, I think it's a cat. Was I right? Oh, I was right, great. And then it says, does it, for the opposite case, when it gets it wrong. And if it gets it right or wrong, it changes the way it interprets that image each time to be a little bit better at getting the right answer. And when you're done with that process, you have what's called a trained model. So the model looks a little bit different. It's learned stuff. And the information it learned is basically in the model itself. And so then you want to use that model. That model is basically deploy. We would call this model deployment, meaning you're going to put it out into the wild so that it can start to make decisions. You might spend some time making sure it runs really well on the computer you need it to run on. But basically, once it's trained and set up, you can now start doing what's called inference. And inference is where some new data that this model's never seen before is given to it. And it says, hey, what do you think this is? And if this model is really well trained, and this is actually a picture of a cat, it would say cat. And if it's not a picture of a cat, it would say dog. Now, one interesting thing to keep in mind is if I only trained this model with dogs and cats, but then I gave it the picture of a raccoon, what do you guys think it would do? You think it would say cat? It would guess, error, dogs, cat, 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 cat. Now you guys are probably saying cat because you might think a raccoon looks similar to a cat, maybe. And you might not be that far off, but it's kind of anyone's guess as to what this thing would do because it only knows what you've trained it. So if it doesn't know what a raccoon is, it will just make a guess, and it could be cat or it could be dog, but you really don't know. So these trained neural networks are only as smart as the data you give them, and they don't know anything else because, again, they started off as just this dumb, unknowing model on the other side, and it only knows about what you told it. All right, so with all that in mind, now we kind of know a type of AI, this deep learning. Do you guys think that deep learning or AI could help with video games and graphics? Yes, 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 it could. Okay. All right, so we're going to talk about one way. There's actually lots of ways it can help, and this talk could go on for several hours, but we don't have that much time. So we're going to talk about one way, which is pretty fun, and we're going to talk about generative adversarial networks, which are a type of neural network, and those are a lot of big words. So what do you guys think a generative adversarial network is? Just, you could guess, or maybe you know. An enemy bot. How to code a function. All right, so let's break it down. We can maybe know what these words mean. All right, so generative adversarial network. So generative, if we just look at the word generative, that kind of means something that creates. It's generating something, a generator. Adversarial usually means a rival or a challenger. And then network, as we just learned, is a computer model used in AI. It's basically the math that the computer uses to learn things from data. So we have a computer AI model that creates things and has some type of adversary or adversarial component, some sort of rival. So let's break this down. So generative adversarial models or networks are often referred to as GANs. So you guys might hear that. And the way you create a GAN, it's really a two-player game. You have this first player, and he's the generator. And then you have, oh, sorry, I thought I turned all these off. You have the first player, and he's the generator. And then you have the second player, and he's called the discriminator. So these are the two players of the game. And the goal is for player one to take random numbers. Just think of a random number and produce an image. And it wants to basically create realistic images. And player two's job is to look at those images and say, are those real images? I don't know if they're real images. But how's player two going to know what a real image looks like? We're going to give it training data, which is basically, in this example, real pictures of faces. So we're going to teach player two how to figure out what a real face looks like. And so we basically train it. We show him a lot of examples, just like we did with the cats and the dogs, and say, this is a face, this is a face, this is what faces look like. And then he knows a little bit of stuff, right? So player two is a little bit smart at this point. And it says, hey, player one, these are really green. They don't really look like faces. I don't think any of these are faces. You're not very good at making faces. And so player one says, maybe I should make stuff less green. And so player one, it starts training a little bit. And it's like, all right, I got to make things less green to trick player two. And so then basically player one starts to make things that look less green. Okay, player two says, that looks different, but I'm going to train a little bit more to make sure I really, really know what a face looks like. And it says, you know, that doesn't really look like a face either. It doesn't have any eyes or mouth or hair. And so then it says, hey, generator, it's a little bit better, but it's still not right. You need to learn some more. And so then player one does some more training. And so this back and forth basically just keeps going on and on, where they're playing off of each other. And then eventually the generator is able to create better faces, and it's all from feedback from player two. And so these two players, or networks in this case, play off against one another. And so what you end up with are faces. So all of these faces are fake. None of these are actual people. And some of them actually look really good. Let's kind of zoom in on some of these guys. So those look pretty good. The hair looks pretty good. The light in the eyes looks really good. We've got shadows. None of these are real people. These are not, like, we didn't go take these pictures. But then it's not a perfect process. And every once in a while, we get what we call the monsters. And the monsters are things that don't look like people. They look very, very silly. And so this can be a little bit of a game to figure out which ones are good and which ones are bad. So that's kind of fun. But what do you guys think this could be used for? When I said it could be used in graphics. Games, I don't know, games, gaming, to make characters, photo recognition software. Yeah, those are all really good guesses, guys. So yeah, so it's one thing to be able to create a bunch of different looking people that aren't real people, and I can just sort of ask a computer to give me a lot of examples. But to really make it impactful, you have to start to be able to control what these people look like. And if it's just a random process, give me a random number and I'll give you a random person, it's a bit hard to control. So some of the research Nvidia has been doing is on coming up with different ways to control the random people that get created. Now, again, none of these people are real. And what this is kind of showing is how you can combine each of these people in the top row with the person in the bottom row. And so you get these different variations of people. And so now you sort of have a little bit more control over what the people look like. And now it's starting to become more useful for maybe advertising or game development or video game, well, I just said that, or movie generation, things like that. You can also do this for, I think I have to pause this. You can also do this for other things. You don't necessarily have to do it just with people. We've done it with cars, and these are basically bedrooms, and you can control the network, different parts of the network. That's what these words on the side are referring to, different parts of the neural network. You can tweak and control slightly, and then you can get different results. So let me see if I can zoom ahead. It's getting a little laggy on my end as well. And maybe even a more useful thing, go to here, is it would be really cool if we could decide how old this fake person is going to be. And so can we control age? It turns out we can. We can make young people turn old and old people turn young. Yeah, all of this stuff is fake. They're fake cars, fake bedrooms, fake people. This was all trained on a GPU. These neural networks that can now, particularly GANs, that can now create all this training data. Because after you train it, then you can say, okay, now just give me all the fake people you know how to make, or all the fake cars you know how to make. Another thing that might be useful is maybe we want to make people smile or be sad and change their expressions. This is a very complex process in graphics when you're making video games expression. So this is all pretty interesting. I'm doing pretty good on time. We have about 10 minutes. And so I thought what we would end with is Nvidia's actually put some of these technologies up onto a website. Let me pause this. And you guys can play with some of these concepts online. But this is a website, is another type of GAN where you can draw in really simple colors and sort of object types. And then the GAN basically imagines what that should look like. And so you'll get the site in a minute. We can do a new one where maybe we want to draw a mountain. So I'll pick on landscape mountain, and then I'm going to draw a big mountain over here, and then fill it in with mountain. And then maybe we want to have some water go by this mountain, like here. And then we'll fill it in with mountain. And then we'll draw some clouds. This actually looks exactly like the other thing I drew. I should change this up a bit. Hold on. Let's make it, let's add some fog. Let's see what happens if we add, oh no, snow, maybe snow. Okay, and then if you push this button, it's gonna go, oh wow, that made a very foggy, snowy mountainside with a cloud. Here, let's do another new one. Let's put a building, maybe. Oh, I made the whole thing building. Let's do sky first, building. Let's do a house. And then maybe a wall. And some ground here. And let's do a cloud. Let's see what this looks like. Okay, so this is a GAN where you tell it, I want things of this type, and it imagines, it comes up with suggestions of those things. It makes a brand new image that's never been seen before. So this is its concept of a building with a brick wall, and the cloud's pretty good, and the ground is pretty good. And so these are, you guys can go to this website and play to your heart's content. The one thing you do need to make sure is there's a checkbox down here. It'll give you a little button, but you have to hit that first. So yeah, and that was really the end of what I was going to talk about today, and I was going to leave any time for some questions. This one's pretty easy. What is Nvidia? So we're the company that makes GPUs. So that is what we do. We make GPUs and all of the software you need to use them for either graphics or AI or whatever it is. Okay, what's the difference between, well, we don't need to talk about RAM. Do some computers not need a GPU? You don't always need a GPU. If you're not doing big graphics things, then it's not necessary. The CPU can handle it. But if you're playing a big video game or you would like to train an AI algorithm, then right now you do need a GPU. All right, what do transistors do? So transistors are teeny little components of a circuit board. They literally just take in electrical current, and they take in two currents, and they basically can decide if one side's higher than the other one. And that's how a computer decides if something's a 1 or a 0. And computers speak in 1s and 0s. That's the language they use. It's binary. They represent numbers in 1s and 0s, and then combinations of those 1s and 0s mean letters. And that's how you tell the computer what to do. So they're like the fundamental little base unit building block of a chip that lets us control computers, basically. So hopefully that answered what is binary. Oh, isn't it true that most video games are made by motion capture? So yeah, motion capture is a way, and that's basically where you need to have characters in a video game do stuff like run around and crouch and jump and climb on rocks and all those types of things. And some ways of doing that is to hire an actor, and they put on this funny suit with like basically glow in the dark ping pong balls on it, and they run around this big stage. The problem with that can be, though, is that you have to know exactly what your character is going to do And you have to make the actor do that, because otherwise they'll video them doing all of this stuff. And then artists, really highly trained artists, will take all of that video and turn it into parts of the video game, so that when you push a certain button or combination of buttons, your character will do that. But if all of a sudden you tell the character, I want you to run and then crouch and then jump, if they haven't captured a video of a person doing that, what do you tell the character to do? And so there is actually a lot of research right now of coming up with ways to train AI models to sort of be able to predict what a character should do and do that automatically, or learn it from watching a lot of different motion capture videos. Okay, the GPU is just pictures and the CPU is the code. Well, no, you still have to code the GPU. You have to tell, it takes instructions in the form of code, just like the CPU does. It's just a different set of instructions. So the CPU does, its whole mission is to make the computer useful for you and have things move quickly. So you can have a web browser up, you know, you can have Chrome up, you can have your email up, you can have your chat program up, and you can do all of these things and bounce between them. And so it can handle a lot of different instructions, whereas the GPU handles a different set of instructions that are more specific for how do I make a picture show up on the screen. And so that's the type of code you write. The language that we've developed to program our GPUs is called CUDA, C-U-D-A. And so programmers write CUDA code, and it shows up in lots of different languages like C++ and Python and C. And that's how a developer would tell a GPU what to do. Okay, maybe one more. Oh, ray tracing. I don't really get it. What's ray tracing? So ray tracing, don't feel bad. It's a pretty complex idea, but the main concept is, if we want to have a computer create an image, like we want to say, all right, computer, there's a round ball, the light is above it, and I'm standing here. Can you tell me what the ball would look like? You need to have some type of way of simulating how that light interacts with that ball and how it would look to you as a person. And so the way people do that is with the ray tracing concept. They basically say, okay, if light would follow, they simulate light as a ray, which is basically just the direction the light's traveling in. And they say, okay, I've hit this big circle and it's made of rubber, and I know how rubber interacts with light. And so you do some math, so I know how much light bounces back in this direction and maybe up and down and sideways, but I'm over here. So you're calculating how much of that light would actually reach my eyeball as a person. And in the simulation, we simulate that eyeball as a camera, basically. And so that act of moving all of those rays through the scene, because you can simulate, you need a lot of different rays to fully capture all of the light in a scene. That is the hard part, doing all of that at once and fast enough.
How did you get a job at Nvidia?
Oh, that is a very long story, my friend. It was not on purpose. It might be a story for another day, but basically I started using deep learning to solve my own problems. So the area I work in is actually in satellite imaging. So I know a lot about the type of cameras they put on satellites and airplanes that image the Earth. So if you've gone to Google Earth ever and you see all those pictures where you can kind of see your house from the top, those are collected by satellites and airplanes, and the cameras that they put on those are pretty interesting and different. And a lot of times people want to say, okay, find me all the trucks in the city or something like that. And the best way to solve that problem, it turns out, is with deep learning. So I started doing that. I started using deep learning to solve some problems with the data that I worked with. And Nvidia had an interest in being able to do that better. And so they found me and hired me.
So what button do I have to press before I can start drawing?
Before you're speaking, before you can start what?
Start drawing the picture on the app.
There's a little, at the bottom of the screen, there's a red banner and it says, check this box if you agree. So if you click that button, then you're good to go. And then you should be able to use the buttons on the left. The button on the top with the plus sign makes a new blank canvas. The bottom button is like a paintbrush, and the paint pail fills in an object. I think this little dropper sort of helps you select a single color, and then this is the arrow is the undo button, and you can pick which type of thing you're doing on this left side here, and you can change the brush shape and size. You can do all sorts of things. It's pretty fun to play with.
Can you use Nvidia to create a 3D world, like similarly like we did here?
Yeah. So a lot of that's part of the simulation process, and there's a bunch of different applications that people use to do this. So artists, graphic designers, and game builders will go in and they'll build 3D worlds where they draw and make shapes and decide what their world looks like. And then they start to say what each of the things are in these worlds. This is a rock. This is this color paint. This is grass. That's called giving it texture. And so what's that?
If there's a link to a website that could do that, could you send it?
Well, these are typically pretty big applications that you would run on a big computer. I don't know if there's any web-based 3D sort of software.
Do you have the name of an application?
These would be called like Maya or Katya's for like designing cars. There's Autodesk makes a lot of these, but these are big professional applications. Oh, there is a free one called Blender, Blender. That's an open source rendering application. It's pretty complex. I have no idea how to use it myself, but that is an application that's free and you can download it. It does require a pretty big machine, otherwise it's just a bit slow, but you could play with that if you wanted to start learning stuff.
I was like wondering if like there's a way that you can like change the color without it like forcefully making the color.
Are you talking about just in general or in the GAN game? I'm sorry, what did you, I didn't hear you. You mean you want to change like whether or not this is, the way you can change the color is, I don't think you can't say, I want clouds to be blue. It's sort of decided for you. And the color is sort of telling you what type of background or image to create. So like now I've made a bunch of fog, and I don't think you can control it necessarily.
Great. Well, with that, I think that finishes May's talk. Thank you so much, May. That was amazing.
Oh, you're most welcome. I had a lot of fun.
So much interesting things and interesting technologies, and you guys asked great questions as well. So we will, I know that because that's the thing, right? The video, we want the video to show really well, so they're high resolution, and we know that there been some lag. So we will actually record the video. We have already recorded. They will be on our website. And so you can actually go to our website or go to our YouTube channel to watch the whole thing. Those videos are truly amazing. It's, you know, some of these things, I don't know if you know, like something like this used to take like weeks and even months.
Oh, I mean, that's why movies like Pixar movies take years. There's farms of GPUs, giant buildings filled with computers just to create those scenes. And now we're slowly shrinking the amount of compute you need into smaller and smaller boxes and making it go faster and faster. But yes, they're called render farms. They're literally buildings of computers whose whole job is to make pictures look good.
Yeah, it's amazing how these things become even like real time with the GPU.
Yeah.
So yeah, totally amazing. And hopefully, May, you'll be back to talk more about AI. I know we
I'd love to come back. I'm sorry I didn't get to everybody's questions. I see a lot of please.
Yeah, some really good questions. But we will be doing more of these classes, and we'll talk more about these topic. And hopefully, May will be back again soon to talk more about it. We do have another talk coming up. You know, every week or so, we have a new talk about different aspects of computer science. The next one is super fun as well. So we all have phones. We probably spend too much time on the phones these days. And you guys might have wondered, how do you actually build apps on the phone, right? A lot of it is similar to how you might do things for a computer, but a lot of it are also different. So next time we have a friend from Google, and he has actually been working on Android for almost 10 years, and he will come talk about how apps on mobiles are made, and we might even build a little project for your phone. So definitely look forward to seeing all of you guys there, and I'm sure you will enjoy that as well. With that, I want to thank you again, May, for the fantastic talk. And thank you everyone for joining. You guys were awesome, and we'll see you guys again next time.
Thank you.
All right, bye.
Bye.